Greetings, viewers. Today, we are going to pull back the curtain on one of the most vital yet misunderstood components of our modern world, the high-voltage power transformer. We often see these massive, humming metallic boxes tucked away in substations behind barbed wire fences, but few truly appreciate the complex engineering marvel that happens inside. To help us visualize this, we have created a specialized 3D glass model that allows us to look directly through the outer casing and observe the internal components in action. At its core, a power transformer is a silent workhorse designed for one primary purpose: to change the voltage of electricity. This is a critical step in the journey of power from a generating station to your home. Electricity is generated at relatively low voltages, but to travel hundreds of miles over transmission lines without losing too much energy to heat, that voltage must be stepped up to hundreds of thousands of volts. Once it reaches your neighborhood, the transformer steps it back down to a safe level for your appliances. Looking through our transparent model, the first thing you will notice are the massive, intricately wound coils of copper. These are the heart of the machine, known as the primary and secondary windings. They are not actually connected to each other by wires. Instead, they are linked by an invisible force, electromagnetic induction. When high-voltage electricity flows through the primary winding, it creates a fluctuating magnetic field. This magnetic field is focused and channeled by the transformer's core, which is made of thousands of thin, laminated sheets of silicon steel. This core acts like a highway for the magnetic flux, guiding it through the center of the secondary winding. As the magnetic field passes through the secondary coil, it induces a current, effectively jumping the energy from one circuit to another while changing its voltage based on the ratio of turns in the wire. Because these machines handle immense amounts of energy, they generate a significant amount of heat. If left unchecked, this heat would melt the insulation and destroy the transformer. This is why you see those large radiator-like fins on the outside. Inside, the entire assembly is submerged in a specialized mineral oil. This oil serves two critical functions. First, it acts as a high-grade insulator, preventing electricity from arcing between the high-voltage components. Second, it acts as a coolant. As the oil heats up around the core and windings, it rises and circulates through the external cooling fins. The surrounding air cools the oil, which then sinks back to the bottom to begin the cycle again. This natural convection, often assisted by fans, keeps the transformer at a stable operating temperature. Looking toward the top of our 3D model, you will see the high-voltage bushings. These porcelain or composite insulators act as the gateway for electricity to enter and exit the tank. They are designed with a shed-like shape to ensure that even in heavy rain, there is always a dry path to prevent electrical leakage or flashovers to the grounded metal tank. Near these bushings, you might notice a cylindrical tank called a conservator. This is a vital safety feature. As the oil heats and expands during heavy loads, it needs a place to go. The conservator provides that extra space, ensuring the main tank remains completely full of oil at all times to prevent air pockets. In modern power grids, flexibility is key, which brings us to the unload tap changer, or OLTC. This is a complex mechanical switch that can change the connection point on the windings while the transformer is still energized. This allows the utility company to fine-tune the output voltage in real time, compensating for fluctuations in demand throughout the day and ensuring your lights stay at a constant brightness regardless of how much power the rest of the city is using. Every component we see here, from the massive steel core to the smallest cooling pipe, is a testament to over a century of electrical engineering. Without these silent giants, our long-distance power grid simply could not function. By using this transparent view, we can finally appreciate the elegant dance of magnetism and fluid dynamics that keeps our world powered. Thank you for joining us on this deep dive into the inner workings of the high-voltage transformer.